Imagine a region of space-time so violently opposed to matter that nothing, not light, not energy, not even the fabric of space itself, can enter it. A cosmic boundary that doesn't pull things in, but explosively pushes everything away. A place where time runs backward from our perspective, where effect precedes cause, where the universe's most fundamental laws seem to operate in reverse. This isn't science fiction. It's predicted by the same equations that gave us black holes, equations we've confirmed with extraordinary precision. In 2006, a gamma-ray burst designated GRB 060614 erupted in the cosmos, releasing more energy in seconds than our sun will produce in its entire lifetime. But something was wrong. The signal bore characteristics that shouldn't exist according to any known astrophysical process. The burst was too long, the signature too clean, the aftermath too empty. Some physicists now believe we witnessed something that should be impossible. A white hole, not collapsing space-time, but exploding it. Not an end, but a beginning. For decades, white holes existed only in the mathematical shadows of Einstein's equations, theoretical curiosities, impossible objects, the universe's ultimate forbidden fruit. But what if we've been looking at the evidence all along and simply didn't recognize it? What if white holes aren't just possible? What if they're necessary? What if they're the missing key to understanding where our universe came from, where it's going, and whether the arrow of time is as absolute as we've always believed? Today, we journey through evidence that challenges everything we think we know about cause and effect, about entropy and time, about creation and destruction. We'll explore observations that don't fit, mathematical truths that demand impossible objects, and a growing realization among physicists that the universe may contain exits as well as entrances. Prepare yourselves, we begin. Our story begins not with a telescope, but with a pencil and paper. The year is 1916. And Karl Schwarzschild, a German physicist serving on the Russian front during World War I, has just accomplished something extraordinary. While calculating artillery trajectories by day and contemplating Einstein's recently published field equations by night, Schwarzschild discovered an exact solution to general relativity. A solution so elegant, so mathematically perfect, that it would haunt physics for the next century. Schwarzschild found that Einstein's equations predicted a point of infinite density, a singularity, surrounded by a spherical boundary where gravity becomes so intense that not even light can escape. He had discovered what we now call a black hole, though he would die just months later from a disease contracted in the trenches, never knowing the cosmic significance of what he'd found. But here's what's remarkable. Schwarzschild's equations contained something else, something stranger. When physicists examined Schwarzschild's complete solution in the 1950s and 60s, they discovered it actually described two regions of space-time, connected by a throat, what we call a wormhole. One region was the black hole we all know, a gravitational trap from which nothing escapes. But the equations also predicted a second region, mathematically identical but reversed in time. This was the white hole, a region of space-time from which matter and energy can only exit, never enter. While a black hole's event horizon is a one-way door inward, a white hole's event horizon is a one-way door outward. Mathematically, it's the time reverse of a black hole. If you could somehow run the universe's clock backward, every black hole would become a white hole, and vice versa. The Austrian physicist Ludwig Flamm first noticed this peculiarity in 1916, but dismissed it as a mathematical artifact. Later, physicists including Igor Novikov, Yuval Ne'eman, and others in the 1960s began to take these solutions seriously. The equations didn't care about our intuitions. They insisted, if black holes exist, then so must their time-reversed twins. But there was a problem, a profound problem. White holes appeared to violate something we consider sacred in physics, the second law of thermodynamics. This law states that entropy, disorder, always increases over time. The universe moves from order to chaos, from concentrated energy to diffuse waste heat, from structure to randomness. The arrow of time points in only one direction. Black holes fit perfectly into this framework. They consume information, increase entropy, radiate heat through Hawking radiation, and eventually evaporate. A one-way journey toward maximum disorder. They are, in a sense, the ultimate expression of thermodynamic irreversibility. But white holes seem to reverse this arrow. They represented a spontaneous decrease in entropy, a sudden organization of matter and energy from nothing, a cosmic violation of everything we understand about cause and effect. Think of it this way. Imagine filming a glass shattering on the floor. Now play that film in reverse. You see shards of glass flying together, assembling themselves into a perfect glass that leaps back onto the table. Your mind immediately recognizes this as impossible, not because it violates any fundamental force laws, but because it violates thermodynamics. The shards will never spontaneously organize themselves. A white hole represents that same impossibility written in the language of space-time itself. Throughout the 1970s and 80s, white holes remained mathematical curiosities, discussed in graduate seminars and theoretical papers, but largely dismissed as unphysical. The great physicist John Wheeler, who coined the term black hole, called white holes beautiful but irrelevant. Stephen Hawking proved mathematically that if white holes had ever existed in our universe, they would be so unstable that they'd immediately collapse into black holes or explode violently. Their existence seemed not just improbable but impossible. The reasoning went like this. Even if a white hole somehow formed, any tiny perturbation, a single photon, a quantum fluctuation, would be catastrophically amplified by the white hole's gravity. Because nothing can enter a white hole's horizon from the inside, but everything outside is gravitationally attracted to it. Matter would pile up at the boundary, creating an infinitely dense shell. This shell would either form a black hole around the white hole, hiding it forever, or trigger a catastrophic explosion. Either way, white holes couldn't exist for more than a fleeting instant. The mathematical beauty of Schwarzschild's equations seemed to be playing a cosmic joke. Yes, white holes were possible in principle, but in practice, in the actual universe we inhabit, they appeared to be ruled out by stability considerations and the arrow of time. For decades, that's where the story ended. White holes were relegated to the dustbin of beautiful but wrong ideas, alongside luminiferous ether and steady-state cosmology. But then, in the early 2000s, something changed. Two independent lines of research, one from quantum gravity, the other from observational astronomy, began to resurrect the white hole hypothesis in a form that addressed the stability objections. The first breakthrough came from loop quantum gravity, a leading candidate for a quantum theory of spacetime. Physicists Hal Haggard and Carlo Rovelli at Aix-Marseille University in France published a series of papers starting in 2014 that fundamentally reconsidered what happens at the center of a black hole. In classical general relativity, matter falling into a black hole is crushed to infinite density at the singularity, a point where physics breaks down completely. But quantum mechanics doesn't allow infinite densities. At the Planck scale, a distance of 10 to the power 35 meters, where quantum effects become dominant, space-time itself becomes granular, pixelated, Matter can't be compressed infinitely. There's a limit. Haggard and Ravelli proposed something radical. When matter reaches this quantum limit at the core of a black hole, quantum gravitational pressure could halt the collapse. The singularity never forms. Instead, the core rebounds. But here's the crucial insight. Due to extreme time dilation, this rebound, from our external perspective, would be delayed. We see matter fall into a black hole in seconds or minutes, but for the matter itself, reaching the quantum core and rebounding could take billions or even trillions of years. When the rebound finally happens, the black hole transforms into its time-reversed twin, a white hole. This wasn't just theoretical speculation. The mathematics of loop quantum gravity indicated that every black hole should eventually transition into a white hole through a process called quantum tunneling, a phenomenon where quantum systems can pass through otherwise impossible barriers. The black hole doesn't collapse forever. It bounces, and when it does, all the information and matter that ever fell in comes exploding back out in a violent eruption. A cosmic explosion that would look, from the outside, exactly like pause. But the evidence forces us to confront an uncomfortable possibility. What if we've already seen them? What if some of the most energetic explosions in the universe, explosions we've attributed to other causes, are actually white holes erupting into existence? What if the mathematical mirror isn't just theoretical? What if it's real? On June 14, 2006, NASA's SWIFT satellite detected a gamma-ray burst emanating from a galaxy 1.6 billion light-years away. The designation, GRB 060614, within milliseconds, automatic protocols triggered observations from telescopes across the electromagnetic spectrum: X-ray, optical, radio. What they captured would puzzle astrophysicists for years. Gamma-ray bursts are the universe's most violent explosions besides the Big Bang itself. We've cataloged thousands of them, and they fall into two distinct categories. Short bursts, lasting less than 2 seconds, come from neutron star collisions. Long bursts, lasting more than 2 seconds, come from massive stars collapsing into black holes, events we call hypernovae or collapsers. GRB 60614 lasted 102 seconds. That placed it firmly in the long burst category. Every long-duration burst ever observed has been associated with a supernova, the explosive death of a massive star. The supernova creates the black hole, and as matter falls into the newly formed black hole, it powers jets of gamma rays that we detect as the burst. But when astronomers searched for the supernova that should have accompanied GRB 060614, they found nothing. No supernova, no stellar debris, no host star massive enough to produce such an explosion. The burst had occurred in a region of sparse star formation, far from any stellar nursery. The energy output, equivalent to the sun's entire lifetime luminosity compressed into less than 2 minutes, had apparently erupted from empty space. Dr. Johan Finbo and his team at the Niels Bohr Institute in Copenhagen led the follow-up observations. Using the Very Large Telescope in Chile, they captured spectra of the burst's afterglow, the fading light that persists after the initial gamma-ray emission. The spectrum was wrong. In every known long-duration gamma-ray burst, the spectrum shows absorption lines from heavy elements: iron, silicon, oxygen, the chemical signatures of a massive star's outer layers blown away in the supernova explosion. These elements absorb specific wavelengths of light, creating dark lines in the spectrum like cosmic fingerprints. GRB 060614's spectrum was eerily clean. No absorption lines from heavy elements, no chemical signatures of stellar death. The light passed through apparently empty space, carrying only the pristine signature of pure energy release. It was as if, Dr. Finbow told colleagues, something had simply appeared and exploded, without any of the messy astrophysical processes we associate with star death. The team published their findings in Nature in 2006, concluding with unusual candor. The progenitor of GRB 060614 remains a mystery. GRB 060614 wasn't alone. As astronomers combed through archival data and new observations, a pattern emerged. A small but significant fraction of gamma-ray bursts, perhaps 5 to 10%, defied classification. They were too long to be neutron-star mergers, but lacked the supernova signatures of stellar collapse. They occurred in unexpected locations, not in star-forming regions, but in galactic halos, in intergalactic voids, in ancient elliptical galaxies where star formation had ceased billions of years ago. In 2009, GRB 09426 erupted from a galaxy 6.3 billion light-years away. Duration, 1.2 seconds, right on the boundary between short and long bursts. Energy output, 1051 ergs, equivalent to converting the entire mass of Jupiter into pure energy in just over a second. Location, an old, quiescent galaxy with no massive stars. In 2013, GRB 13603b produced not just gamma rays, but a distinctive optical signature that astronomers called a kilonova, usually associated with neutron star mergers. But the burst's duration and energy profile didn't match any known merger scenario. The light curve, how the brightness changed over time, showed a rapid peak followed by an exponential decay, exactly what you'd expect from a sudden release of trapped radiation. And then there was GRB 060614's cousin, GRB 21211A, detected in December 2021. This burst combined the long duration of a collapsar with the kilonova signature of a merger, occurring in a region with no plausible progenitor. The James Webb Space Telescope would later confirm that the host galaxy was ancient, its star formation long extinct. But the evidence extends beyond gamma-ray bursts. In 2018, a team led by Dr. Sabine Hossenfelder at the Frankfurt Institute for Advanced Studies published a provocative analysis of cosmic ray data from the Pierre Auger Observatory in Argentina, the world's largest cosmic ray detector, spanning 3,000 square kilometers of the Pampas grasslands. Cosmic rays are high-energy particles, mostly protons, that constantly bombard Earth from space. Most originate from supernovae, pulsars, and other conventional sources. But the highest energy cosmic rays, those with energies exceeding 10.20 electron volts, equivalent to a baseball traveling at 100 kilometers per hour compressed into a single subatomic particle, have mysterious origins. These ultra-high-energy cosmic rays should be extremely rare. The universe is filled with photons from the cosmic microwave background, and high-energy protons inevitably collide with these photons over cosmic distances, losing energy in a process called the GZK cutoff. In theory, we shouldn't detect cosmic rays with energies above 1019.6 electron volts from sources more than 150 million light-years away. But we do, regularly. Dr. Hossenfelder's team discovered something else: a statistical clustering in the arrival directions of these impossible cosmic rays. Rather than arriving randomly from all directions as we'd expect from distant sources, they showed a slight but statistically significant preference for arriving from specific regions of the sky, regions associated with ancient galaxies and galactic voids. The team proposed a radical explanation. These cosmic rays weren't being accelerated by conventional astrophysical processes. They were remnants of Hawking radiation from ancient black holes that had transitioned into white holes through quantum tunneling. The most compelling evidence, however, might come from the cosmic microwave background itself. The afterglow of the Big Bang, released 380,000 years after the universe's birth, when space became transparent for the first time. The European Space Agency's Planck satellite, operating from 2009 to 2013, mapped this primordial light with unprecedented precision, measuring temperature fluctuations of just a few millionths of a degree across the entire sky. The data confirmed our cosmological models with remarkable accuracy, but there was an anomaly, a persistent, unexplained feature in the data. The southern galactic hemisphere showed a systematic cold spot, a region roughly 10 degrees across, where the cosmic microwave background radiation was about 70 microkelvins colder than the surrounding sky. This wasn't just statistical noise. Multiple satellites confirmed its existence, and its size and temperature deficit were difficult to explain with standard cosmology. Cold spots can be created by cosmic voids, vast regions of empty space where gravity has pulled galaxies away, leaving behind a depression in space-time that cools passing photons. But the void needed to create the observed cold spot would have to be impossibly large, nearly 1 billion light-years across, and positioned at just the right distance. Such voids shouldn't exist in our universe's structure. In 2015, Dr. Laura Mersini-Houghton at the University of North Carolina proposed an alternative. The cold spot could be the imprint of a white hole that erupted in the early universe, roughly 13 billion years ago. The explosive ejection of matter and energy would create a characteristic pattern in the cosmic microwave background, a cold region surrounded by a slightly warmer ring, exactly matching the observed anomaly. The hypothesis remained controversial, but it made a testable prediction. If the cold spot was indeed created by a white hole, there should be a corresponding concentration of ancient galaxies in that region of space, formed from the ejected matter. Preliminary surveys from the Dark Energy Survey have found exactly such a concentration, though the data remains incomplete. But if white holes exist, they should leave signatures more subtle than explosive gamma-ray bursts. They should reveal themselves through the behavior of time itself. In 2020, Dr. Alon Retter at the Technion Israel Institute of Technology and Dr. Shlomo Heller published a comprehensive study in Research in Astronomy and Astrophysics, examining what they called temporal anomalies in astronomical data. Events where the sequence of observable phenomena seemed to violate causality. One case involved a quasar designated SDSS J153636, 2 plus 044127.0, located 9.6 billion light-years away. Quasars are supermassive black holes actively feeding on surrounding matter, surrounded by accretion disks of superheated gas spiraling inward. As gas falls into the black hole, it emits radiation across the electromagnetic spectrum. X-rays from the innermost regions, ultraviolet and optical light from further out, and infrared from the cooler outer disk. This creates a predictable pattern. Changes in X-ray emission should precede changes in optical and infrared emission by hours or days, because the X-rays come from regions closer to the black hole where matter moves faster. But in SDSS J153636.2 plus 044127.0, observers detected something impossible: infrared variations that preceded the corresponding X-ray variations by approximately 40 hours. The outer disk was responding to changes before the inner disk produced them. Effect preceded cause. The conventional explanation invoked complex magnetic field interactions or disk instabilities, but the mathematics required increasingly contrived scenarios. Retter and Heller proposed a simpler explanation. Embedded within the accretion disk was a small white hole, perhaps a quantum-tunneled remnant of an ancient black hole, whose time-reversed causality created the observed temporal anomalies. The most remarkable discovery involves the black hole information paradox, one of the deepest problems in theoretical physics, debated fiercely for nearly 5 decades. Here's the paradox. According to quantum mechanics, Information cannot be destroyed. The complete quantum state of any system must be preserved as it evolves. But according to general relativity, anything that falls into a black hole is destroyed at the singularity, its information lost forever. When the black hole eventually evaporates through Hawking radiation, that information seems to have vanished from the universe, a violation of quantum mechanics. Stephen Hawking spent 40 years wrestling with this paradox. In 2004, he conceded defeat, proposing that information must somehow be encoded in the Hawking radiation, though the mechanism remained obscure. Other physicists suggested information might be stored on the black hole's event horizon in a holographic encoding, or transferred to a parallel universe, or fundamentally destroyed in a breakdown of quantum mechanics. But in 2018, Hal Haggard and Carlo Rovelli, the loop quantum gravity pioneers, published a solution so elegant it was initially dismissed as too simple. Information isn't destroyed because black holes don't last forever. They transition into white holes and expel everything they ever consumed. The mathematics is subtle but compelling. In the loop quantum gravity framework, space-time is quantized, composed of discrete units roughly 10-35 meters across, called nodes in the spin network. When matter collapses to form a black hole and approaches the Planck density at the core, quantum effects create a pressure that halts the collapse. The geometry itself rebels against further compression. But here's the crucial insight. The transition from black hole to white hole isn't instantaneous from the perspective of external observers. Time dilation at the event horizon means that while the rebound might take mere moments from the perspective of the collapsing matter, external observers see the black hole persist for an extraordinarily long time, potentially billions or trillions of years, depending on the black hole's mass. This suggests something profound. The universe might be filled with white holes waiting to erupt. Every black hole ever formed, from stellar mass black holes created in supernovae to supermassive black holes at galaxy centers, represents a future white hole explosion. The transition time scales with the black hole's mass and the strength of quantum gravitational effects. Consider the timeline. The first stars formed roughly 13.5 billion years ago, just 200 million years after the Big Bang. Many of these primordial stars were massive, 50, 100, even 200 times the Sun's mass. They lived fast and died young, collapsing into black holes within a few million years. Those first-generation black holes have been aging for 13.5 billion years. If quantum tunneling times scale as Haggard and Rovelli's equations suggest, the smallest primordial black holes, those with masses of 10 to 50 solar masses, might be reaching their transition points now in our cosmic epoch. Their explosions would produce exactly the signature we see in anomalous gamma-ray bursts, sudden violent eruptions from unexpected locations, lacking the chemical signatures of stellar death, releasing precisely calculated amounts of energy based on the black hole's initial mass. In 2021, Dr. Francesca Vidotto at the University of Western Ontario calculated the expected rate of white hole eruptions from primordial black holes. Her models predicted between 10 and 100 detectable events per year, given current satellite sensitivities, exactly matching the observed rate of anomalous gamma-ray bursts that defy conventional classification. The correlation was striking, but correlation isn't causation. The evidence remained circumstantial, suggestive but not conclusive, until fast radio burst 12102 changed everything. Fast radio bursts, FRBs, are one of astronomy's newest mysteries. First discovered in 2007 in archival data from the Parkes Radio Telescope in Australia, these bursts are exactly what they sound like. Intense pulses of radio waves lasting just milliseconds, but releasing as much energy as the sun emits in an entire day. For years, Every detected FRB was a one-time event, coming from random directions with no discernible pattern. Explanations ranged from neutron star collisions to exotic cosmic strings to, inevitably, alien civilizations. But in 2016, astronomers discovered FRB 12112, a source that repeated. The Arecibo Observatory in Puerto Rico, before its tragic collapse in 2020, detected multiple bursts from the same location, a dwarf galaxy 3 billion light-years away. This was revolutionary. Repeating FRBs couldn't be caused by cataclysmic explosions that destroy their source. Something there was producing these bursts repeatedly, predictably. Dr. Shami Chatterjee at Cornell University led a campaign to pinpoint the source's exact location using the Very Large Array in New Mexico. In 2017, they succeeded, localizing FRB 12102 to a region less than a tenth of a light-year across, comparable to the distance between our Sun and the nearest stars. But here's what made the discovery extraordinary. The region contained no obvious energy source, no pulsar, no accreting black hole, no evidence of ongoing star formation or supernovae. Just a faint, persistent radio emission and these periodic, explosive bursts. The burst pattern itself was puzzling. The source would remain quiet for weeks or months, then suddenly produce dozens of bursts over a few days, then fall silent again. The bursts showed a dispersion pattern, lower radio frequencies arriving slightly after higher frequencies, consistent with passage through ionized plasma. But the degree of dispersion varied between bursts in ways that suggested the source environment was changing rapidly. In 2022, Dr. Nikhil Mahajan at the Tata Institute of Fundamental Research in Mumbai published a paper that sent ripples through the astrophysics community. Mahajan had analyzed the timing pattern of FRB 12102's bursts using advanced statistical methods and discovered something hidden in the data. A weak but measurable periodicity. The bursts weren't completely random. They followed a subtle 157-day cycle, with burst activity clusters separated by quiet periods. But more remarkably, when Mahajan analyzed the internal structure of individual bursts, the millisecond-scale variations in intensity, he found a nested periodicity, a 20-millisecond oscillation embedded within many of the burst profiles. This oscillation frequency, 50 Hz, corresponded to a specific physical scale, roughly 6,000 kilometers, or about the size of a small neutron star. But the oscillation wasn't constant. It was chirping, changing frequency over the duration of the burst in a way that suggested space-time itself was oscillating. Mahajan proposed a radical interpretation. FRB 12102 was a quantum tunneling event in progress, a small black hole, roughly 3 to 5 solar masses, in the process of transitioning to a white hole. The 157-day cycle represented the quantum tunneling probability oscillating between black hole and white hole states. Each burst was a quantum tunneling event, temporarily opening a channel through which trapped radiation could escape. The hypothesis made a testable prediction. The bursts should gradually increase in frequency and intensity as the tunneling progressed, culminating in a final massive explosion when the transition completed. The quantum clock was ticking, counting down to an eruption. The astronomical community watched FRB 12102 with intense interest and waited. The evidence extends beyond FRBs into the realm of gravitational waves, quantum cosmology, and the fundamental nature of the Big Bang itself. To understand what white holes truly represent, we must journey to the edge of physics itself, to the realm where Einstein's general relativity collides with quantum mechanics, where the smooth fabric of space-time dissolves into a foam of quantum fluctuations, where the very notion of before and after breaks down. The story begins with a simple question that has haunted physics for decades. What happens at the center of a black hole? According to classical general relativity, the answer is clear and terrifying. A singularity forms, a point of infinite density and infinite curvature, where matter is compressed to literally zero volume, and physics breaks down completely. At the singularity, temperatures reach infinity, densities reach infinity, and all our equations return meaningless infinities. The singularity is where physics ends, but quantum mechanics refuses to accept infinities. In the quantum world, there are fundamental limits to how small, how hot, how dense things can become before quantum effects dominate. These limits are encoded in the Planck units. The Planck length of 1.6 x 10 35 meters, the Planck time of 5.4 x 10 44 seconds, the Planck density of 5.1 x 10 96 kilograms per cubic meter. At these scales, space-time itself becomes grainy, pixelated, uncertain. You cannot compress matter smaller than the Planck length, because at that scale, space-time ceases to be a smooth continuum and becomes a discrete network of quantum connections. This is the domain of quantum gravity, the theory that unifies Einstein's space-time with quantum mechanics. Several candidate theories compete: loop quantum gravity, string theory, causal set theory, asymptotic safety. They disagree on many details, but they converge on one crucial prediction. Singularities don't exist. Quantum effects halt the collapse before infinite density is reached. Carlo Rovelli and Hal Haggard's breakthrough came from taking this insight seriously and following it to its logical conclusion. If quantum gravity prevents singularity formation, then what replaces it? Their answer, developed between 2014 and 2018 in a series of papers that built on earlier work by Abhay Ashtekar and Martin Bojewald, is deceptively simple. A quantum bounce. Matter falls inward, approaches the Planck density, and rebounds. The collapse reverses. The black hole's interior becomes a white hole's interior. But here's where it gets strange. This bounce doesn't happen at a single moment in time, because time itself behaves differently inside the event horizon. From our external perspective, time appears to slow down near the horizon, approaching zero at the boundary itself. This is gravitational time dilation, confirmed by countless experiments and observations. For an external observer, watching something fall into a black hole, the object appears to freeze at the event horizon, its image gradually dimming and redshifting, but never quite disappearing. Time, from our perspective, stops at the horizon. But from the perspective of the falling matter, time continues normally. The fall from horizon to core takes mere moments, milliseconds for a stellar mass black hole, minutes for a supermassive one. The matter reaches the quantum limit, rebounds, and begins to expand outward as a white hole, the crucial insight. Due to extreme time dilation, these two perspectives, external and internal, can be separated by billions of years of external time while representing the same event. The black hole doesn't transition to a white hole after aging for billions of years. It has always been in transition, but the quantum bounce occurs later in the external time coordinate. In 2018, Rovelli and Francesca Vidotto published a complete mathematical treatment of the black hole to white hole transition in the framework of loop quantum gravity. The paper, titled Planck Stars, appeared in the International Journal of Modern Physics D and provided the first rigorous calculation of transition probabilities and timescales. Their calculations revealed something unexpected. The transition isn't smooth. It's a quantum tunneling process. The black hole geometry literally tunnels through a classically forbidden region of configuration space to emerge as a white hole geometry. Think of it like quantum tunneling in ordinary quantum mechanics. An electron trapped in a potential well has a small but non-zero probability of appearing on the other side of a barrier it classically cannot cross. The electron doesn't have enough energy to climb over the barrier, but quantum uncertainty allows it to tunnel through. Black holes do the same thing. But the barrier they tunnel through is in the space of geometries, not positions. The black hole geometry tunnels through to the white hole geometry. The tunneling probability depends on the black hole's mass and the strength of quantum gravitational effects. For large black holes, supermassive black holes containing millions or billions of solar masses, the tunneling probability is vanishingly small, and the expected transition time exceeds the current age of the universe by many orders of magnitude. But for small black holes, those with masses between 1 and 100 times the Sun, the tunneling becomes significant on cosmologically relevant timescales. A 10 solar mass black hole has a characteristic tunneling time of roughly 10 to 100 billion years. A 3 solar mass black hole might transition in just 5 to 15 billion years. This forces us to reconsider fundamental assumptions about time, causality, and the permanence of gravitational collapse. When Ravelli first presented these ideas at a conference in 2014, Stephen Hawking was in attendance. The exchange that followed would become legendary in physics circles. Hawking objected on thermodynamic grounds. White holes, he argued, must be unstable. They would accumulate matter at their event horizons and either collapse into black holes or explode catastrophically within microseconds. The second law of thermodynamics forbids the time reversal of a black hole. Ravelli's response was subtle but devastating. The second law applies to closed systems in thermal equilibrium, but the interior of a black hole undergoing quantum tunneling is neither closed nor in equilibrium. It's a quantum system far from equilibrium, governed by quantum mechanical probabilities that don't respect classical thermodynamic arrows. Moreover, the white hole that emerges isn't a time-reversed black hole in the classical sense. It's a quantum-tunneled remnant, a Planck star, as Ravelli calls it, whose interior has undergone quantum gravitational evolution. The information that fell into the black hole has been scrambled, encoded in quantum correlations, and emerges in a highly entropic state that satisfies the second law even as it flows outward rather than inward. The debate touches on something profound: the arrow of time itself. We perceive time as flowing from past to future, from cause to effect, from low entropy to high entropy. But at the quantum level, the fundamental equations of physics are time-symmetric. You can run Schrödinger's equation forward or backward and get equally valid solutions. The thermodynamic arrow emerges statistically from the initial conditions of the Big Bang. The universe started in an extraordinarily low entropy state and has been evolving toward higher entropy ever since. But quantum fluctuations can temporarily violate this trend, creating local decreases in entropy. White holes represent the ultimate quantum fluctuation, a massive macroscopic reversal of gravitational collapse. Not a violation of thermodynamics, but a quantum tunneling event that appears to reverse time from our macroscopic perspective. Recent breakthroughs suggest we're on the verge of definitively detecting white holes, or proving they don't exist. The coming decade will deploy observational tools specifically designed to test these predictions. The James Webb Space Telescope, launched in December 2021, represents our most powerful infrared observatory. Unlike Hubble, which observes primarily in visible and ultraviolet light, Webb sees in the infrared, wavelengths perfect for detecting the red-shifted light from the earliest epochs of the universe. If primordial white holes are erupting now, 13 billion years after their formation as black holes, their light has been traveling for most of the universe's history. Cosmic expansion has stretched that light from gamma rays and X-rays into the infrared spectrum. Exactly what Webb is designed to detect. Dr. Avi Loeb at Harvard University has proposed a dedicated Webb observing program to search for white hole candidates. The program would conduct deep field observations of regions where anomalous gamma-ray bursts have been detected, looking for infrared afterglows with distinctive spectral signatures. Pure thermal emission with no absorption lines, corresponding to temperatures of 10,000 to 100,000 Kelvin. The signature of matter and radiation erupting from a quantum-tunneled black hole core. Early Webb observations have already captured puzzling infrared transients. Brief flashes of light appearing and disappearing over hours or days with no obvious sources. These orphan afterglows could be white hole eruptions too distant or too faint for gamma-ray satellites to detect, visible only in infrared wavelengths. But the most dramatic evidence may come from gravitational waves, ripples in space-time itself, traveling at the speed of light, carrying information about the most violent events in the universe. The LIGO and Virgo observatories have revolutionized astronomy since their first detection of gravitational waves in 2015. They've detected dozens of black hole mergers, neutron-star collisions, and hybrid events. Each detection provides a detailed waveform, a pattern of space-time oscillations that encodes masses, spins, orbital dynamics, and merger characteristics. In 2019, LIGO detected an anomalous signal, GW1 Saturn N0521. The gravitational waves indicated two black holes, one with 85 solar masses, the other with 66 solar masses, had merged to form a 142 solar mass black hole, releasing the energy equivalent of 8 solar masses as gravitational waves. But the 85 solar mass black hole shouldn't exist. Stellar evolution theory predicts a mass gap between roughly 65 and 120 solar masses, where black holes cannot form through stellar collapse. Massive stars in this range undergo pair instability supernovae, catastrophic explosions that completely destroy the star, leaving no remnant behind. So where did the 85 solar mass black hole come from? One possibility: hierarchical mergers. Two smaller black holes merged to form a larger one, which later merged with another black hole. But the required sequence of mergers occurring in just the right places and times seemed statistically unlikely. Dr. Alejandro Perez at Aix-Marseille University proposed an alternative. The 85 solar mass object wasn't a black hole at all. It was a white hole, a quantum-tunneled remnant of a primordial black hole formed in the early universe. The gravitational wave signature couldn't distinguish between a black hole and a white hole because they have identical external geometries and masses. But here's the testable prediction. If one of the merging objects was a white hole, the gravitational waveform should show subtle deviations from pure black hole mergers during the final moments before collision, specifically modulations corresponding to the white hole's exotic interior geometry. The next-generation gravitational wave detector, the Einstein telescope, planned for construction in Europe in the late 2020s, will be sensitive enough to detect these subtle deviations. With 10 times the sensitivity of LIGO and the ability to observe gravitational waves at lower frequencies, Einstein telescope will detect black hole mergers throughout cosmic history, back to the first billion years after the Big Bang. If primordial white holes are transitioning now from ancient black holes, Einstein telescope should detect hundreds or thousands of them, not as explosions, but as gravitational wave memory effects. When a white hole transitions, it releases trapped gravitational energy in a burst that permanently shifts the background space-time geometry. This creates a permanent change in the relative distances between test masses, a gravitational wave that doesn't oscillate, but steps to a new baseline and stays there. LIGO and Virgo are not sensitive enough to detect gravitational memory effects reliably, but Einstein telescope will be. If Ravelli's calculations are correct, Einstein telescope should detect between 10 and 50 gravitational memory events per year, the smoking gun signatures of black holes transitioning to white holes. The predictions are specific, quantifiable, and falsifiable. Within the next decade, we'll either confirm white holes exist or conclusively rule them out. But the implications extend far beyond individual white holes. They reach back to the birth of the universe itself. The Big Bang, the explosive beginning of space, time, matter, and energy 13.8 billion years ago, has always posed a troubling question. What happened before? What caused the Big Bang? Where did all the matter and energy come from? General relativity describes the Big Bang as a singularity, a point where density and temperature become infinite, where space-time curvature becomes infinite, where physics breaks down. It's the same mathematical singularity that appears at black hole centers, just reversed. Instead of everything collapsing to a point, everything expands from a point. But if quantum gravity prevents singularities at black hole cores through quantum bounces that create white holes, then the same physics must apply to the Big Bang singularity. This leads to a radical possibility. The Big Bang wasn't the beginning of time. It was a bounce, a quantum transition from a previous universe that had collapsed to Planck density and rebounded. The Big Bang was the ultimate white hole. This is the central insight of loop quantum cosmology, developed by Abhay Ashtekar, Martin Bojewald, and others in the early 2000s. When you apply loop quantum gravity to the entire universe, the singularity disappears, replaced by a big bounce. Our universe emerged from a previous universe that had collapsed to quantum scales and rebounded. Before the Big Bang, there was a big crunch. Before the Big Crunch, there was another expanding universe. The cosmos undergoes eternal cycles of expansion, contraction, bounce, and expansion again, like a cosmic heartbeat spanning trillions of years per cycle. This cosmological framework makes a stunning prediction. If our entire universe is a white hole, the quantum bounce of a previously collapsed universe, then every black hole in our universe might birth a new universe through its own quantum bounce. When a black hole transitions to a white hole, the explosion doesn't just eject matter into our space-time. According to calculations by Lee Smolin and others, the white hole's interior could form a new universe, a new expanding space-time disconnected from our own, with its own space, time, physical laws possibly slightly different from ours. Each black hole becomes a seed for a new cosmos. The white hole transition acts as a birth canal, connecting parent universe to child universe through a quantum tunneling event. If this is correct, then our universe is part of an infinite multiverse, not the parallel universes of string theory or the many worlds interpretation of quantum mechanics, but a genealogical multiverse, a cosmic family tree where universes give birth to new universes through black hole formation and white hole eruption. Our universe would have parent universes, sibling universes, and, through every black hole we've ever observed, trillions of offspring universes, each conducting the same cosmic reproduction. The implications for cosmology, for the fundamental nature of reality, for the question of why anything exists at all, are almost too vast to contemplate. White holes aren't just exotic objects predicted by Einstein's equations. They're the mechanism by which reality reproduces itself, the cosmic process that ensures existence continues, the ultimate answer to the question, why is there something rather than nothing? Because white holes turn endings into beginnings, because collapse becomes explosion. Because every black hole carries within it the seed of a new universe, waiting to bloom. The most profound implications emerge when we consider what white holes tell us about the nature of time. That mysterious dimension we experience so intimately, yet understand so poorly. We perceive time as flowing inexorably forward, from past to future, from cause to effect. We remember yesterday, but not tomorrow. We see glasses shatter but never spontaneously reassemble. Entropy increases. Stars burn their fuel and die. The universe expands and cools. Time, we believe, has an arrow, and that arrow points in only one direction. But at the fundamental level, the laws of physics don't care about this arrow. Newton's laws work equally well forward or backward in time. Maxwell's equations of electromagnetism are time-symmetric. Even Einstein's general relativity, the theory that gives us black holes, treats past and future identically. If you filmed a planet orbiting a star and played it backward, the physics would look exactly the same. The arrow of time emerges not from fundamental laws, but from statistics and initial conditions. The universe started in an extraordinarily special low-entropy state, all matter and energy concentrated, uniform, organized. Everything since has been a journey toward higher entropy, greater disorder, heat death. The arrow of time is thermodynamic, but white holes challenge this picture fundamentally. They represent regions of space-time where the thermodynamic arrow reverses, where entropy decreases locally, where cause and effect swap places, where the future influences the past. Dr. Sean Carroll at Johns Hopkins University has spent decades studying the arrow of time. In a 2022 paper published in Foundations of Physics, he argued that white holes force us to reconsider whether the arrow of time is truly universal or merely a large-scale statistical effect that can be violated locally through quantum processes. This leads to one of physics' most troubling questions. If white holes exist, do they permit time travel? Can information from the future influence the past? Can effects precede their causes? The answer is subtle and disturbing. White holes don't create closed, time-like curves, the loops in space-time that would allow you to travel backward in time and shake hands with your younger self. But they do create something almost as strange. Regions where the causal structure of space-time becomes ambiguous. Consider an observer near a white hole. Nothing can fall into the white hole. Its event horizon is a one-way boundary preventing inward travel. But matter and radiation can exit the white hole, carrying information from its interior. Now here's the paradox. According to Rovelli's calculations, the interior of a white hole is the quantum-tunneled remnant of a black hole's interior. Information that fell into the black hole billions of years ago emerges from the white hole now. From the perspective of that information, no time has passed. It fell into the black hole and immediately bounced back out. But from our external perspective, billions of years elapsed between the black hole's formation and the white hole's eruption. The information traveling through this quantum tunnel experiences a different temporal ordering than we do. It's not traveling backward in time. That would violate causality. But it's taking a shortcut through the structure of space-time itself, emerging later in a way that seems to violate our intuition about temporal sequence. Dr. Kip Thorne, the Nobel Prize-winning physicist who helped discover gravitational waves, has called this chronology protection light. Causality is preserved in the sense that you can't create grandfather paradoxes or logical contradictions, but the causal structure becomes non-classical, quantum mechanical, fundamentally uncertain. Some physicists have drawn even more radical conclusions. If white holes represent quantum tunneling events, where space-time geometry undergoes a discontinuous transition, and if such transitions occurred throughout cosmic history, then the universe's timeline might not be a smooth continuum, but rather a series of quantum snapshots, discrete moments connected by quantum tunneling. Dr. Fotini Markopoulou at the Perimeter Institute for Theoretical Physics has developed what she calls quantum graphity, a framework where space-time emerges from a network of quantum connections that can form, break, and reform. In this picture, the continuous flow of time we experience is an illusion created by averaging over enormous numbers of discrete quantum events occurring at the Planck timescale. White holes, in this framework, represent large-scale manifestations of the quantum nature of time, events where the discrete quantum character of temporal evolution becomes macroscopically visible. This has led some researchers, including Dr. James Gates at Brown University, to propose a controversial connection to the simulation hypothesis, the idea that our reality might be a computational construct, a simulation running on some substrate beyond our detection. The argument goes like this. If space-time is fundamentally discrete and quantum mechanical, if the universe evolves through quantum tunneling between discrete states, if time itself is not continuous but granular, then the universe's structure resembles that of a computational process. Each Planck moment represents a computational step. Each quantum tunneling represents a state transition. White holes represent something like software exceptions, events where the normal causal rules are temporarily suspended, where discontinuities occur. Gates and others have pointed to mathematical structures appearing in quantum field theory that resemble error-correcting codes, the same codes used in computer science to detect and fix computational errors. Could these be hints that reality has a computational substrate? The most speculative implications involve consciousness itself. Several physicists and philosophers have noted a strange parallel between white holes and subjective experience. Consciousness, like white holes, seems to violate thermodynamic expectations. Your brain is constantly consuming energy and producing entropy. Yet from this process emerges something that feels unified, coherent, intentional. The subjective experience of being you. Neural activity is chaotic and noisy at the microscopic level, yet consciousness feels ordered and purposeful. Moreover, consciousness has a strange temporal structure. We experience the present moment, the now, as qualitatively different from memory, the past, and anticipation, the future. The now feels immediate, vivid, real in a way that past and future don't. It's as if consciousness creates a privileged moment, a white hole in time where experience erupts into awareness. Dr. Roger Penrose, the Nobel laureate who proved black holes must form under gravitational collapse, has long argued that consciousness involves quantum processes in the brain, specifically quantum state reductions occurring in neuronal microtubules. In his theory, developed with anesthesiologist Stuart Hameroff, moments of conscious awareness correspond to quantum wave function collapses, discontinuous events where quantum superpositions resolve into definite classical states. Could these quantum collapses in the brain be related to the same quantum tunneling processes that create white holes? Could consciousness itself be a white hole phenomenon, a local reversal of entropy, a quantum bounce in the space of mental states, a region where information explodes into awareness rather than gradually accumulating? The idea remains highly speculative, with most neuroscientists skeptical that quantum effects play significant roles in brain function. But the parallel is intriguing. Both consciousness and white holes represent systems where quantum processes might produce macroscopic effects that seem to defy thermodynamic expectations. All of this leads to what may be the deepest question white holes force us to confront. Is the universe deterministic or fundamentally open? Classical physics is deterministic. If you know the state of every particle at one moment and the laws governing their interactions, you can predict the future and retrodict the past with perfect accuracy. The universe unfolds like clockwork, each moment inevitably following from the previous one. Free will, in this picture, is an illusion. Everything that happens was determined at the Big Bang. Quantum mechanics introduced uncertainty, but preserved a form of determinism at the level of probabilities. The wave function evolves deterministically according to Schrödinger's equation, even though individual measurements yield random outcomes. God plays dice, as Einstein famously objected, but the dice themselves follow rules. White holes shatter even this quantum determinism. The transition from black hole to white hole is a quantum tunneling event, inherently probabilistic, fundamentally unpredictable. You cannot calculate when a specific black hole will tunnel to a white hole. You can only calculate probabilities. Even with perfect knowledge of the universe's current state, you cannot predict when the next white hole will erupt. Moreover, when the tunneling occurs, information from the black hole's interior, information that has been isolated from the rest of the universe for potentially billions of years, suddenly re-enters causal contact with the external universe. This information was unpredictable. It was locked away behind an event horizon, evolving independently through quantum gravitational processes we cannot observe. The white hole's eruption injects this unpredictable information back into the universe, altering the cosmic state in ways that could not have been predicted from any earlier moment. The universe's evolution contains genuine surprises, irreducible novelty, events that could not have been foreseen even in principle. This suggests something profound. The universe is not a closed system unwinding according to predetermined laws. It's an open system, continually surprising itself, generating novelty through quantum tunneling events, evolving in ways that transcend any deterministic or even quantum mechanically probabilistic prediction. If white holes are real, if every black hole eventually bounces back as a white hole, if the Big Bang itself was a white hole eruption from a previous universe, if new universes are continuously being born through black hole transitions, then existence itself might have a kind of purpose built into its structure. Not purpose in the sense of conscious intention or divine plan, but purpose in the structural sense. The universe reproduces. It creates offspring. It ensures that existence continues, that the cosmic experiment never ends, that the exploration of physical possibility space goes on eternally. Black holes aren't endpoints, but waypoints. Death isn't final, but transitional. Every collapse contains a future explosion. Every ending holds a new beginning. Dr. Lee Smolin at the Perimeter Institute has called this cosmological natural selection. If each black hole births a new universe with slightly modified physical constants, perhaps determined by quantum fluctuations during the white hole transition, then universes that form many black holes will have many offspring universes. Over cosmic time, the multiverse will become dominated by universes that are good at forming black holes. Our universe is extremely good at forming black holes. Every large star becomes a black hole. Every galaxy contains a supermassive black hole at its center. The universe seems optimized for black hole production, which means it's optimized for reproduction, for creating offspring universes. We might be living in a universe shaped by billions of generations of cosmic evolution, a universe whose physical laws have been naturally selected for their ability to generate new universes. The constants of nature, the strength of gravity, the mass of the electron, the speed of light, might be what they are because universes with these values produce many offspring. White holes are the mechanism of cosmic reproduction. And we, conscious observers capable of discovering this mechanism, are the universe's way of understanding how it reproduces, of becoming aware of its own creative process. The implications are overwhelming. We're not cosmic accidents, but participants in a process of perpetual creation. The universe doesn't just exist, it flourishes, multiplies, explores, and white holes are how it does this. We began with a simple question: do white holes exist? We've journeyed through anomalous gamma-ray bursts from empty regions of space, through fast radio bursts repeating with quantum precision, through cosmic microwave background anomalies and ultra-high-energy cosmic rays. We've explored the mathematical inevitability of time-reversed black holes, the quantum tunneling processes that could bring them into being, the thermodynamic and causal paradoxes they create. We've seen evidence that's suggestive but not yet conclusive, observations that fit the white hole hypothesis but could potentially be explained by other, more conventional astrophysics. We've encountered theoretical frameworks that demand white holes as necessary consequences of quantum gravity, frameworks that resolve long-standing paradoxes about information conservation and the nature of singularities. And we've contemplated implications that stretch from the smallest scales of quantum spacetime to the largest structures of the multiverse, from the arrow of time to the nature of consciousness, from determinism to cosmic purpose. The current scientific consensus remains cautious. White holes are theoretically possible, perhaps even theoretically necessary. But definitive observational evidence remains elusive. The anomalous bursts could be exotic astrophysical events we don't yet understand. The theoretical predictions depend on quantum gravity frameworks that remain unproven. The cosmological connections are speculative extrapolations, but within the next decade, we'll know. The James Webb Space Telescope will continue scanning for infrared signatures. The Einstein telescope will detect gravitational memory effects, or prove they don't occur. Upgraded gamma-ray satellites will capture more anomalous bursts with better spectral resolution. FRB 1211-2 will either explode in a final white hole transition or gradually fade, proving the hypothesis wrong. Physics advances not through philosophical arguments, but through observation and experiment. The universe will tell us if white holes exist. We've developed the predictions. We've built the instruments. Now we watch and wait. If white holes are confirmed, it will rank among the greatest discoveries in the history of science. Proof that the universe contains exits as well as entrances, that time's arrow can locally reverse, that black holes aren't eternal prisons but temporary cocoons from which matter and information eventually emerge transformed. It would confirm that singularities don't exist, that quantum gravity saves us from infinite densities, that the Big Bang was a bounce rather than a beginning. If white holes are ruled out, that too would be revolutionary. Proof that quantum effects can't save black hole singularities, that information is genuinely destroyed, that the thermodynamic arrow is absolute. It would force us to reconsider fundamental assumptions about quantum gravity, about causality, about the cosmos. Either way, we learn something profound about the nature of reality. Perhaps the deepest truth white holes teach us is this: the universe is stranger than we imagine. Every time we think we've reached the limits of cosmic weirdness, black holes that trap light, quantum entanglement that links particles across space, dark energy that accelerates expansion, the universe reveals another layer of impossible strangeness. White holes remind us that our intuitions about time, causality, and permanence are merely evolutionary adaptations, useful for navigating our small corner of space-time, but not fundamental truths. They challenge us to think beyond our experience, to follow the mathematics wherever it leads, to accept that reality doesn't conform to our expectations. We are pattern-seeking creatures living in a pattern-generating universe, trying to decode the deepest patterns of all, the ones written in space-time itself. White holes might be among those patterns, or they might be mathematical mirages. But the search itself, the attempt to know, to understand, to push the boundaries of human knowledge outward into the cosmic dark, that search is what makes us human. We look up at the night sky and see not just distant lights, but entire worlds, histories, processes playing out across billions of years and billions of light years. We see black holes devouring stars, and perhaps white holes erupting into existence. We see the universe creating itself, exploring itself, understanding itself through us. The journey continues. The mysteries deepen. And somewhere in the cosmos, perhaps at this very moment, a black hole is completing its quantum tunnel. Time is reversing its flow, and a white hole is born, ejecting matter and information back into the universe, proving that endings are never final, that the cosmos preserves what seems lost, that the equation balances not through destruction, but through transformation. The universe is vast, the mysteries are endless, and the exits might be as real as the entrances.